All right, and we're recording. Welcome to Helicopter Pilot Study Group number 17. Today we're going to talk about low G. We're going to talk about mast bumping. And I'm sure we're going to get into a lot of other topics too. There's been a lot of good conversations on the thread. So the point of this study group is for pilots of all skill levels from entry to, thousands of hours to get together, pick tasks from the ACS, pick topics of interest, present on them, really open up the opportunity for students to get comfortable or for pilots to get comfortable presenting. And then we kind of discuss the topic, discuss the presentation technique, and then just kind of transition into other topics. My name's John. I'm the founder of this group. Today we have Steven's going to start us off with a little conversation or with his discussion on it's mast bumping, right? Or low.
Yeah, I mean it does concern mass bumping.
Okay.
It's a presentation that I'm associated with a community college in my flight training, and
Yep.
so there's the class I'm in right now. It's a systems class, and so for the presentation, my professor gave me a topic, and it has to do with mass bumping. It's pretty Robinson heavy because that's what I fly, and that was what the system concerned. So it's got a lot in there, but it's not necessarily just about that.
No, that's great. Yeah, you're free to discuss whatever feels right, and I'll let you go ahead and take it away. If you have any questions about the operation of Discord, let us know. But take your time, and I'll let you take it away, Scott or Steven. Thanks, man.
Oh yeah, okay, sounds good. Let me see how this works here. Played around with it a little bit.
All right, I'll fire up your stream.
Let's see
There you
here.
go.
The only way I was able to get it to work, unless somebody can tell me otherwise, is to share the screen and then come over here to my presentation. So can you guys see that all right?
Yeah, that does work. The other option is to
Yep.
pop out, but the way you're doing it right now does work. The pop out in the lower right.
Mhm.
But go ahead and share your screen.
Sorry.
That worked really well.
Okay,
Yep.
sounds good.
Yep. Excellent.
Well, I suppose I'll real quick, just a little bit, tiny little bit about me. I'm in private. So as far as the presentation goes, I'm definitely subject to mistakes. So feel free to call me out. That's what this is about, like John said. So, but I'm currently at Leading Edge, same school that Jay's at, working on private here. So getting close to my stage 2. But anyway, that's where I'm at with my training. So this presentation, like I mentioned before, it's for my systems class. So the topic that my professor gave to me was the new Robinson horizontal stabilizer design. So Robinson's changing things up a little bit. So like I said, it's got some low G mass pumping stuff in here, but primarily it's about this new stabilizer design. So we'll hop right in here. So just have a little bit here, what we'll cover. I have a comparison of the old and new stabilizer. Got a couple pictures there to show the difference, what's changing. And then I do go a little bit, like I said, into the low G mass bumping, some dangers and symptoms. Then I kind of delve into the history behind the change, why Robinson's changing, some of the studies, accidents, and investigations that went on leading up to the change, and then finishing off with the results. So this is the old stabilizer. It's still being used by a lot of helicopters because they just came out with the system. But this was the original design. It goes all the way back to 1979. From what I saw, that was the release of the first R22. So as you can see, it's an asymmetrical stabilizer, and it's only on the right side of the tail cone. It's directly opposite the tail rotor, as you can see. So that was the original horizontal stabilizer from, like I mentioned, from all the way from the beginning up till now. And then the new one, it's a little zoomed out here, but you can see this new stabilizer. This is the new design they're coming out with. So it's a symmetrical stabilizer instead of the asymmetrical previously. The key difference is here, it extends to both sides of the tail cone instead of just the one side like was the original design. Obviously, since they moved it to both sides, they had to move it up, so it's forward of the tail rotor. They're putting these, from what I saw, they're putting these on all the R22s, 44s, and 66s. They're having kits made for all those. So we're just starting here at Leading Edge we're starting to get some of our helicopters with these. So why are they changing? Well, the simple summarized answer is to stabilize the aircraft in a low G situation. That's the basic answer, but obviously we'll get into it a little bit here. So, a little bit about low G. I mean, obviously, a lot of us know about this, but I figured it'd be good to put in, kind of give a quick summary. So, low G, that's when the helicopter experiences less than 1 G. So, basically, less than the regular weight of gravity. Like we're all right now experiencing 1 G. Low G's when the helicopter's experiencing less than that, just like riding a roller coaster. You go down quick, you're experiencing less than 1 G there. So that's what low G is. The common ways to put yourself in a low G scenario, we have cyclic pushovers, abrupt forward input of the cyclic, whether that's terrain following or avoiding a bird, which don't push I've been told don't push cyclic over to avoid the bird. The bird will avoid you. But anyway, so there's cyclic pushovers, and then there's turbulence. Strong vertical updrafts or downdrafts, can give us low G as well. So what happens with low G? Main rotor disc becomes unloaded. So in this unloaded state, the main rotor and the fuselage act independently of each other. How I like to think of it is just like if you're traveling down the road in a car, and you're driving 60 miles an hour, you turn to the right. Well, the car turns. Your body at this time was traveling straight at 60 miles an hour. You kind of shift over to the side. You're changing direction. Well, like for instance, in a cyclic pushover, when you push the cyclic forward rapidly, the rotor disc tilts forward, but the fuselage wants to continue going the way it's going. And so so essentially the rotor disc and the fuselage start to act, independently is in a manner of speaking. So in this unloaded situation, an input from the cyclic will change the orientation of the disc only. So in normal flight, left cyclic, for instance, rotor disc tilts left, fuselage follows and whatnot. However, in this unloaded state, when you put in any cyclic inputs, only the rotor disc, that's all that changes. The fuselage itself doesn't actually follow the rotor in this case. Similarly, the attitude of the fuselage will also be independent of the main rotor. So any attitude changes that the fuselage experiences they're not really being manifested through the rotor system. Like I said, they're, in a manner of speaking, they're independent of each other. So this picture is actually a picture from one of Jay's videos, S473. He was kind enough to let me put it in my presentation, but obviously you can see the down there, the helicopter training videos. This one in particular was from the S473 video. So I wanted to include it. It's a really good diagram, but in the Robinson specifically, like I mentioned, this is a Robinson heavy presentation. But in the Robinson helicopter specifically, we tend to get a right roll. That's one of the main symptoms we get in low G. And with this right roll, like I said, as you can see in the diagram, the rotor disc isn't changing because everything's unloaded from each other. So the fuselage is rolling to the right in this case, but the main rotor disc is staying flat. Now the next really what low G is so dangerous for us in the two-bladed systems such as the R22s and 44s and whatnot. These two-bladed systems, this low G can lead us to mast bumping. So in this case, the really dangerous part here is when we're rolling to the right, our instinct is, we got to fix the roll to the left, or left cyclic. But in the unloaded state, like I said, they're independent of each other in a way. And so as the fuselage is rolling to the right, and you input left cyclic, now that both sections are going in that direction, and now you can get into this very dangerous situation where the hub can contact the mast, leading to, well, in most cases, leading to separation of the rotor disc from the fuselage, and there's not much you can do at that point. So the main point I was making here, especially with this, this right roll, it was the stabilizer on the helicopter. Well, let's see, how should I put this? It was, let's say, the Robinson was a little bit off when they thought they knew what caused the right roll, and they just recently, through some discoveries, discovered there's a different primary reason for this right roll. And so that's kind of what the main point of this slide in particular was, to show we get the right roll. Why do we get the right roll? And that's what's changed with Robinson has discovered some new things. So fast forwarding here to this next slide. Low G and mast bumping. So low G has always been a concern for helicopters with two-bladed teetering rotor systems because of mast bumping. So for anybody who might not fly these or doesn't know much about them, to compensate for the symmetry of lift, our rotor blades they flap, and they flap off of a teetering hinge. So they're pivoting off of that teetering hinge located in the hub, and that's what when you input left cyclic in the situation of low G, it can lead to excessive flapping. That's where we get the possible mast bumping. And this has always been, like I wrote here, that's always been a problem with these two-bladed teetering rotor systems. The Army conducted investigations into low G mast bumping. That was the video that John posted last week. And because they fly Hueys, Cobras and stuff, there's just different Bell products, and they have two-bladed rotor systems. Well, let's see, in my research I saw that from 1967 to 1982, I believe, there were almost 60 accidents that were a result of low G. Over 200 died in those accidents. And so the Army was like, okay, we gotta figure something out here, because obviously we're getting a lot of accidents. So in 1980, they released that training video, and it delved into the causes, dangers, and correct inputs to be made in a low G scenario to avoid mast bumping. It was a very helpful video. It shaped not only the military's understanding of low G and mast bumping, but also the civilian community as well. Let's see here. Now, when they conducted these investigations, they were working with Bell. They were having Bell do a lot of these tests. They were working with Bell since they were Bell products, and so Bell was really helping them out with this. And so then in 1980, they released that video. So in the Army training video, there's one specific claim that pertains to my topic. I mean, obviously they make lots of other great claims and whatnot, but for my topic in particular, one of the main claims that the Army made was that tail rotor thrust acting above the fuselage of the helicopter, or the helicopter CG primarily, is the primary cause of the right roll. So they were saying in this unloaded state, that tail rotor thrust acting above the CG, that was what's causing the right roll in all these helicopters. Now, Robinson's training material at the time concurred with this claim. Like I said, the first Robinson, from what I understand, came out in 1979. So this training video was really helpful to pilots flying the Robinson helicopters as well, because it was applying the knowledge was applying to all two-bladed rotor systems. So all of Robinson's material concurred with this. There were some. So now I wanted to get into a little bit the cyclic inputs. This is something stressed very heavily, not only in my training, of course, but just like Robinson. It's like I posted here. There's some safety notices from Robinson, and all these highlighted parts, all these highlighted texts, that they're all about cyclic inputs. It's a huge deal. In the Army video, that's one of the things they mention the most, it seems like, is what you do correctly and what not to do. And so I just had some excerpts highlighted here. I wanted to mention the top highlighted text in Safety Notice 11 on the right side here. It says that with reduced thrust from the rotor, the decreased control effectiveness can result in the pilot making large control inputs to counteract rolling motion. Low G mast bumping can occur as a result of these improper control inputs. So in my research, one thing, there was an article, very helpful article, that I used in my research. One thing that it claimed was that Robinson stated that left cyclic input was the only way to get mast bumping. That's what the article said. The claim was that Robinson specifically said that without left cyclic input, mast bumping virtually was impossible to get. Like, essentially you would just roll to the right, but the hub wouldn't contact the mast. So that was the claim of the article. I originally had it in my presentation, but then I was like, okay, well, if they're claiming Robinson said it, maybe I should try to look for that. So I looked, typed in Google, tried to find official Robinson documents. I couldn't find anything that specifically said, like a specific quote from Robinson that said that that was the case. I mean, a lot of these excerpts kind of like lead you in that direction. Like I said, the top highlighted text in Safety Notice 11, kind of like it says that it can occur, that mass pumping can occur from improper control inputs, but it doesn't specifically say that left cyclic is the only way to do it. So I decided to take it out of the presentation. So maybe Jay or somebody would know a little bit more about whether or not that's actually true. But that was something the article said. But anyway, I took it out just because I wanted to make sure to be accurate. So then, let's see, we'll get into accidents here, kind of the history, like I mentioned earlier. It seems like every time, a helicopter company changes something or the FAA changes something, it usually seems to always come from an accident, and this is no different. So 1979 to 1992, there were at least, from the research I did, I found that there were at least 24 Robinson helicopter crashes resulting from the loss of main rotor control. Now, these were all R-22s from what I saw. Most were determined to be low G maneuvering or low rotor RPM. So we're starting a trend here. Robinson's, there's just been some crashes. Low G is something that pops up in a lot of them. But the primary, the primary thing that ties these all together is loss of main rotor control. So 1992 to 1995, NTSB launched an investigation into the main rotor control accidents. It was just kind of like, okay, this is occurring frequently enough. We should maybe check in and see if there's something about the design maybe, or something about Robinson specifically that's causing these. In the same time frame, somewhere in there, the FAA commissioned the Georgia Institute of Technology to conduct simulations into the R-22 main rotor system. Nothing significant was discovered. What I mean by nothing significant was that mass pumping at all has been around. It had been around at this point. Like I said, the Army had released their video. So when I say nothing significant, it just means that the system is just susceptible to low G mass pumping. And so it's, that's all that was discovered essentially. It wasn't something like Robinson specifically is having an issue. So one thing that's important about that, this sentence here, though, when the FAA commissioned the Georgia Institute of Technology, the simulation was on the R-22 main rotor system. So that'll be important later, but just wanted to point that out, the main rotor system on these R-22s. Now, in 1995, for a lot of us who fly Robinsons, we would know, the FAA issued several airworthiness directives, some bulletins, and the SFAR 73. For anybody who might not know, SFAR 73, it's a Special Federal Aviation Regulation number 73. It's basically, the FAA issued it. It's directly concerns the R-22s and R-44s with a bunch of mandatory training guidelines, and certain things you have to cover with the Robinson. So, obviously things were happening frequently enough the FAA felt that they had to issue the SFAR 73, and it only applied to the R-22s and R-44s. So I found this table here. Actually, originally I found it because, once again, these two tables here, that they were in Jay's SFAR 73 video on the helicopter training videos. And so he mentioned it. So I took a look, and I found the actual article itself. So essentially what this is, it's a safety risk assessment report on SFAR 73. The FAA commissioned a safety team to look into SFAR 73 and evaluate it. I highlighted some text at the top. So just to clarify, the data included in these tables, it appears, is only incidents and accidents that were in the United States. But what was interesting to me, I just wanted to see some more accidents here, see what I could find. And there were 11 total mass bumping accidents, according to this table, in the United States from 1980 to 2021. So not a lot of mass bumping specifically, but there were some. So that was kind of what I wanted to see here and point out in this slide. So we fast forward to 2016, more accidents. The trend keeps going. So, following 14 crashes by Robinson helicopters, the Transport Accident Investigation Commission, or the TAIC, recommended that the FAA reopen investigation into the two-bladed teetering rotor system due to the frequency of the accidents. 9 of these 14 were a result of low G. From what I saw from my research, the 14 crashes, almost all, if not all of them, occurred in New Zealand. And additionally, from my research, it seems like this happens a lot in New Zealand. Well, 6 of those 14 crashes were from 2015 to 2016 specifically. So just like a lot of frequent accidents. So that this TAIC, once again, they were kind of like recommending the FAA reopen. Like, is there something with Robinson specifically that's causing the frequency of these accidents? TAIC had concerns that about the design. They wanted a study done that would maybe look into some design improvements, see if there's anything about the design that could be improved that could prevent some low G and mass bumping accidents in the future. The FAA didn't reopen this investigation, however. The neat thing, though, I mean, Robinson's a very good company, and so they took the initiative and they actually opened up an investigation. So fast forward a couple of years, 2018. Now, Robinson commissioned the University of Maryland this time, so different university, different entity, to conduct simulation testing of mast bumping in Robinson helicopters. The results were consistent with earlier tests. There were some other studies done, according to the articles I researched. There were some previous studies done, not just the Georgia Institute of Technology, but these ones were the main ones that I thought were relevant to my presentation. But the results, they didn't find anything else, anything new. There was a second planned phase of testing not completed. However, they, for some reason, didn't complete that second phase. So at this point in time, there's been a few different tests. The FAA had a test. The NTSB looked into it. Robinson's took the initiative, and so far there's just nothing that they could find, that they did find at least, that would make Robinson helicopters more susceptible to this condition. So, however, skeptics remained unconvinced. There were concerns from ATSB. ATSB is the Australian Transport Safety Bureau, and the TAIC, that turbulence could cause mass bumping in Robinson helicopters and cause that right roll and mass bumping before a pilot could react. They were, that second planned phase of testing for Maryland wasn't completed. There were still concerns due to the frequency of the accidents that there was something about the design of Robinson. So, like I said, the skeptics still remained. So Robinson, I mean, at the time, Robinson seemed like they were like, okay, well, we've done our research, the FAA's done research, we're kind of, in a manner of speaking, we're washing our hands of it. But eventually they decided to partner with a private company to investigate further. Now, this investigation specifically targeted tail rotor thrust, fuselage inertia, and aerodynamic surfaces. So if you remember, I pointed out the Georgia Institute of Technology, that investigation targeted the main rotor system of the R-22. This investigation with this private company targeted a few different things, which was interesting to me. The result of this testing done by this private company, they found that the asymmetrical stabilizer on the original design of the Robinson helicopters, this asymmetrical stabilizer on the right side of the tail cone was the primary cause for the right roll on Robinson helicopters. So it's kind of like a breakthrough, like, oh, really? So we have found this design feature that might be causing a really rapid right roll. Possibly it could be so rapid that there's just no time to react. So after I read this result, like, okay, so that's why they've changed now. When I first read this, I was like, okay, well, the Army in their video claimed that it was tail rotor thrust. So I was kind of like wondering, does that mean the Army's conclusion was incorrect? So I was just doing some personal digging just to find out, like, okay, well, what would be the reason for the Army's conclusion versus Robinson? What could be the differences here? So I started looking at some pictures and stuff, and obviously pictures don't mean everything, but one thing I noticed, the two key differences about the design of these helicopters was that, like, for instance, the Huey in the top left, the Cobra top right, the tail rotor is above the tail cone. I mean, it's significantly higher than the Robinson tail rotor. The Robinson's is in line with the tail cone. So, that I was wondering, okay, well, the thrust provided by that tail rotor is significantly higher in a couple of these bell products, in the Huey, for instance, and whatnot. So it could be that that tail rotor thrust being that high is significant. That could be the difference. The other thing I noticed was that the stabilizers on these military helicopters, there's a stabilizer that extends to both sides of the tail cone. So just like what Robinson is switching to, these military helicopters already had it. So those were two key design features. I was like, okay, well, that doesn't mean the Army's video is incorrect. It could just be that, I mean, the design is different. When Bell did their testing, when the military asset, was working with them to test, they were testing their product, and their product is designed differently. So that was just interesting to me to see. I mean, it's obviously it's just my observations. It's nothing official, but somebody else might have some more insight into that. So with this new design, the new symmetrical stabilizer is supposed to help stabilize the Robinson aircraft in low G conditions. Now, it doesn't eliminate mast bumping. Robinson has never come out and said, like, okay, with this new stabilizer, you're free and clear. It's working great. It's not that way. It's just meant to reduce the chance of an incorrect pilot input in a low G scenario. Hopefully, the goal is to reduce the rate of the roll, providing more time to react. And the other thing with this is this new symmetrical stabilizer may cause a right or a left roll. That's something Robinson has clarified. Now that you have the stabilizer extending to both sides, it could cause a right or left, not just a right anymore. That's interesting. And then finally, I just wanted to point out, it's just basically a repeat of before. This is an updated safety notice that was revised in 2025 after they came out with this, with the new stabilizer. But the helicopters have a low rotational inertia about the roll axis, and any imbalance in aerodynamic forces will lead to an accelerating roll. The severity of the roll increases significantly with increased airspeed and lightly loaded. It is strongly influenced by the type of horizontal stabilizer fitted to the helicopter. So it says that down there, helicopters equipped with asymmetrical horizontal stabilizers, earlier version, may experience a rapid right roll under low G. Helicopters equipped with symmetrical horizontal stabilizer may experience a less severe roll to the right or left. So doesn't fix the issue. We still need to be aware of it. But hopefully it gives us time to react, time for us to think a little bit instead of just instinctively putting in some incorrect cyclic input to fix the roll. So that pretty much wraps me up. There's just some references here. The articles that I use. There was a case study by TIAC, and then, like I mentioned, the helicopter training videos by Jay and S473, and then the some official Robinson documents and whatnot, and then of course the video of the mast bumping by the Army. But that's mine. That's my presentation for you. So
That was great. Does anybody want to weigh in, make some comments, and I'll follow up. Anybody have any ideas? Any comments they want to make?
Yeah, I just wanted to say, great presentation, Stephen. A lot of good stuff that you put out there, and the PowerPoint was it flowed very well too. One of the biggest things that I'll give my guys when they're trying to give a class is that they'll put too much information on a PowerPoint slide and like tend to read from it, and you didn't do that. You used it to help pace your class. You added a lot of information in addition to what was on there, so it felt more like a conversation and more of that instead of us being lectured to, like it was. It had a natural flow to it, so that was excellent, my dude.
I second that.
thank you very much. Appreciate it. Thank you.
Absolutely.
I have a few notes. Yeah, certainly reflect what Michael said too. I mean, for your first presentation of this caliber, it was outstanding. I think you certainly hit all the topics. It was entertaining. You're accurate in your information, which is good. You weren't bullshitting us, which is nice.
I
Uh,
I I will say I overstressed, overthought. I changed countless times. I was like, oh dang it, I discovered a new thing. I gotta go in here and stuff. So yeah, that was definitely a lot of work, but definitely trying to be accurate because I knew I probably ought to be with the experienced pilots definitely in this Discord. So
yeah, and that's good, and that's really a part of the value of this group is you want to study it and you want to be correct, and you want to, when you present it, you don't want to be out in left field. And what's cool, I think, about a lot of these subjects is the information that you want is there, and once you start to learn it, everybody kind of still has the same knowledge. We're going to dive deep into this today, I imagine, but we're going to pull out a lot of unique intricacies of this topic. But yeah, you nailed it, man. Great job. One thing I want to say is low G and mass bumping are two separate things, and they should be talked about as such. Don't kind of link them together as an independent, or as a cause and react. It's like a cause and reaction, but it's not like they're not synonymous with each other. So you've probably felt low G and not been in a mass bumping scenario. Right? Like you can feel low G in your in the 44, especially if you lower I saw you doing that, Gabe, right? And that's it. If you lower that collective really quick, if you're training for an engine failure or something and you just drop that collective, you're going to feel that low G scenario. That's not necessarily going to cause a mass bumping situation, right?
yeah,
So,
fair.
and it's really, mass bumping is pilot induced, right? Mass bumping doesn't just happen. It's as a result of a pilot input.
Okay,
Yeah.
that's what I was trying to find some excerpt. I just didn't want to necessarily throw it in, but
Mm-hmm.
without having something. But that was one thing I wasn't sure if it was just specifically like that article claimed or not. So
Yeah.
that's interesting. That's good to hear. So
Yeah. Um, the you're right. The Robinson found that they initially thought, based off the Army report, that the tail rotor thrust caused that right roll, and it was primarily a result of the old style stabilizer. So, which is kind of interesting. But in a Huey, it's different, right? Like you said, because they have that full horizontal stabilizer. So it's a little bit misleading, but yeah.
Oh,
John, may I?
note,
Oh, sorry.
if I may. So you were talking about like the non-symmetrical stabilizer of the Robinson, and that the tail rotor for both the Huey and the Huey Cobra are above the stabilizer itself. Taking a look at the 206 here, that used to be the TH67, used to be the Kiowa. We can see that with that new design that Robinson is switching to, it seems to mimic a little bit more as to what Bell's been running for quite some time with the Bell 206 there. So, I mean, they went with that from the original design, as opposed to like with the Huey and the Huey Cobra, like what you were saying. So it's good to see that Robinson's sort of catching up to what Bell did for what I would consider the most analogous to the Robinson design, at least the tail rotor,
Yeah.
and the tail boom portion there.
I have to agree with you in that sense. You know, I've thankfully been able to fly several models of Bells throughout the years, and also Robinsons. Mainly, you know, and I guess I love the way, and let me compliment you first, right? Let's retake the positive first, and then go into the neat and greet. Love the presentation. You know, I felt completely identified. I just came back from Indiana, teaching over there. I'm going to New York next week to do some polishing over there. And unfortunately, so disappointing how little people dives into SFAR 73 as a whole. Nonetheless, when it comes down to low G mass pumping, really, it's scary how many people are flying solo as students and even as flight instructors out there without knowing exactly what the causes of this are. You know, precisely mixing and linking so tightly together low G and mass pumping, where we know now that they are two separate things. you know.
Right.
But I wanted to congratulate you because you brought up the physics behind it, and you're talking about inertia, which is not something usually people talks about at your level. You brought up the thrust. You brought up everything that I hit on my SFAR 73 presentation, and it's not because I do it. It's just because it's the physics behind it, and I think that as pilots we should be prepared for that. So kudos, 100% for all of that.
Thank you very much.
Going back into my tangent with the bells, right? The way that I've been explained through some Bell representatives in the past, especially with the UH1s, so UH1A, UH1B, so Bell 204, 205 series in the civilian world, and Cobras, etc., is that the design decision to put the tail rotor with a 45-degree tail rotor came to two choices. Number one, safety on the ground. They didn't want any more crews running into the tail rotor. It makes it tall enough that they will avoid it. And second off, efficiency. In forward flight, when we look at the path of the helicopter nose down, it makes obviously the tail high. That's why we have the right roll. Oh, perfect. Thank you, John. I'm not at the office. I don't have my props, so apologies for that. And when you're going down, of course, you're going to have a higher setting on the tail rotor position, and it won't interfere as much with the downwash and the vortices that we're producing from the main rotor. So, in the case of the 204, 205, however you want to call them, and the Cobra, right? The real problem was that tail rotor became so efficient when the tail was higher up than that main rotor that the thrust would overcome, okay, and it would produce the right roll in their case. I was also explained at some point that the 206s, so the Jet Rangers, are as susceptible as any other aircraft to mast bumping that are semi-rigid. The saving grace was that they have mechanical flap restrictors that are metal pieces that prevent that from happening, not to extreme cases, right, like what we've seen in Robinson, but that accompanied with the mass of that rotor system, which is greater than what we have, knowing from the low inertia rotor systems we have, it won't produce as much of that low G moment into the main rotor. Or if I explain myself, it will compress that forces less, meaning that it won't get as disengaged as in a Robinson. So then again, just throwing bits and pieces here and there, right? And lovely presentation. Thank you, thank you, thank you.
Yeah,
Yeah, no problem. Thanks.
Terrific, Gabriel. The explanation of the tail rotor on the 204 and 5 makes a lot of sense. The Robinsons do have teeter hinges, as we all know, but they only work to an extent, right? They're kind of flimsy in comparison than the Bells. I had something I was going to say. I forgot. Anybody have anything else you want to discuss? Oh, Triana, I had a question for you.
Yeah, what you got?
Your horizontal stabilizer. If you guys don't know,
Mm-hmm.
Triana's our military Black Hawk PIC, bad dude, and he flies Blackhawks. But your horizontal stabilizer, it moves, right?
Yeah, so
And do you
so
control that
not
manually,
a
or is that automatic?
stabilizer. We refer to it as a stabilator
Stabulator.
because it is programmable through a variety of ranges, full up to full down. Let me see, between 5 and 12 is what we're looking at. Between at the very bottom, 6 and 10 is the top. So yeah, there's a pretty significant arc that the stabilator will travel through in the mode of flight, going from like compensating from the least at like over 100 knots to the most when you're getting down to like hovering flight. And it also programs with your pedal inputs to streamline with, say, like if you have a lot of left pedal put in, it'll go downwards to allow the rotor wash to streamline and like not hit the flat part of the stabilator. So it's programmable for better aerodynamic efficiency.
So it's not through a pedal input primarily. Oh, the pedals do affect it, but it is generally an
Mhm.
automatic input. It automatically adjusts, or you have control too.
Yes.
Both, all three.
No,
Okay.
so we do not have direct control
Okay.
over it. There's a mechanical mixing unit that helps to control that, and then we also have pitch, roll, yaw, and I think it's yaw to pitch that couples up as well. So there's a lot of stuff that's going on behind the scenes up in the hydraulic deck there. So though we can input manual control over it in the case of a flight computer failure.
Mm-hmm.
It typically stays in the auto mode and it automatically programs up and down as accordingly to aircraft inputs.
Yeah, just one more thing to deal with, right?
Yeah,
As if
yeah,
getting shot at is not enough. All right.
right.
Anybody else have anything I want to comment or present? Gabe? Gotcha.
Sorry, I'm an old man. I just don't know how to do things here. I just wanted to add, there was a very interesting article, and I can't remember what magazine. Maybe next time I'll bring it up if that's okay with you
Oh,
guys.
yeah.
About an accident. It was publicized a while back in Australia. That's where it was. So brand new R66. The owner has flown quite a bit of hours in it. It's got autopilot. It's got all the new suite by Robinson. And clearly from the video camera that now we all have to install at our corresponding overhauls, we get to see that the pilot is ferrying his dog, right? They're flying on a cross country. They're starting to descend with the autopilot on while the pilot is taking a phone call or text messaging on his phone, eating, and he's having a lot of divided attention in many different places. Unfortunately, disregarded altitude, so he was flying at about 500 AGL by the time he entered the low G condition he entered due to turbulence, and the helicopter rolled to the right, and the autopilot, which was connected at the time, corrected to the left, and mass bumping occurred. In that situation, both the dog and the pilot perished. Unfortunately, so anytime that an aviator dies or anybody has to die because of our actions is lamentable. But I guess, the eureka moment was the video. Of course, we have great improvements through Robinson. Now we're able to see what the reactions were and how it was done. But one thing that is not talked about enough, I think, it's the over reliance on autopilot nowadays with the Robinsons, how people chooses to ignore their main priority, which is flying, and not disconnecting the autopilot when they're going into turbulent situations, right? Where it's clearly stated in the manual that we should reduce our speed, number one, and that we should definitely have manual control. The current autopilot generations are not programmed to respond to low G mass bumping. I guess that's one of the things that I wanted to add, and the other one is my pet peeve. People criticizes me all the time for saying that I fly like a plane. I like to fly high. If you see all of my flight-aware tracks, you're going to find me. I fly here mainly in Florida. You're going to find me at 2,000, 2,500 feet when I can, because it's far less bumpy. You're going to have far less turbulence usually at those altitudes, bar temperature inversions or any other phenomenon, right? But also, just overall, you're going to have less impact of birds. And I think that Stephen did a great job of mentioning that that's one of the main situations where we would dive down, where you would have a lot of obstacles in the way. So choosing your flight path also does a big thing. Here in Florida, with how many lakes we have, especially now that we have the summer back, our convective turbulence is just sometimes awful to deal with. I was getting a rate of climb with a collective full down the other day on a 44 while I was solo of something like 1,000 feet per minute up. and there's nothing you can do to avoid it except lowering the nose a little, and even though it's tempting, we shouldn't.
Mm-hmm.
So imagine dealing with that low to the ground and passing through a lake instead of having gone a little bit more to the side or knowing where your orographic turbulent areas are going to be.
Mm-hmm.
So I guess my point is that it's really a PIC decision at the end of the day. And I think that a lot of people want to blame the helicopter. Unfortunately, I'm a Robbie guy. I love them to death. People really want to blame the Robinson for everything, but unfortunately, there are a lot of factors that we do control as pilot in command and that we should be taking care of.
Certainly. What is your we talked about this last week, I believe, or the week before, where we we always want to initiate a lot of maneuvers with lowering with collective first, and especially in a descent, we're lowering collective to descend rather than push forward. Now, that being said, when I just on my commercial check ride, the DPE during the unusual attitudes portion, he had me foggle up, and then he goes, all right, hold on. And I'm like, holy shit, what does that mean, right? And so and he just he pushed forward and lowered the collective, and it was low G, and it was all the things that I really now this guy obviously knows how to push the helicopter well, within its limits, but also make it fly, but I was kind of spooked me for a second. I was like, man, I felt that low G, but it wasn't as concerning, I guess, as I anticipated it. But what are your thoughts on really that lowering collective to kind of initiate the descent and initiate aggressive maneuvers? Lowering collective first.
Sorry, you were asking.
Yeah, collectively, but
right?
I kind of geared towards you because you were on that topic.
Oh yeah, I guess from the conversations I've had with certain people at Robinson, and Bob Muse has been involved in some of them, and it's a question I asked because then it was natural for us to think, okay, we can't go into low G, but wait, low G doesn't have to be with a cyclic load, right? So it can also be collective induced.
Yes.
They said that they haven't encountered one single accident where they can attribute the lowering of a collective as a cause for low G mass bumping. Mm-hmm. That's their answer, which I wasn't very convinced for, right? It wasn't necessarily a straightforward, hey, here's the evidence why. But yeah, I mean, we have to enter an auto with full collective down. Yeah. There's no way around it. We have to, if we're in straight and level flight, unfortunately, that inertia is going to feel like we have a low G moment, and we will have a low G moment at that point. But the rotor is stabilized, right? We have instead of having an upward to downward airflow, now we're having the opposite. Now we're having a downward flow, which creates that loading of a rotor that we do when we do an aft cyclic movement, right? So I guess it stabilizes a little bit more that way.
I'd like to also point out that if we do get into that low G scenario, the pilot input if there's a roll to the right, the pilot input to instinctively potentially push to the left to counteract, that's more of that's a reaction rather than a response, right? And so it's good to differentiate between the two, and we train to respond to a input rather than react to an input. And I think you see that a lot of times in a lot of scenarios, especially with potentially pulling mixture instead of carb heat, right? That's a reaction, right, rather than the correct response. But so see that Jay popped on. Both Jays are on video. So I like your tool. I saw you have a little toy there. I have a friend who made this for me, and I asked him specifically to make me a rotor system that can flap like this. Yeah, and it will actually strike the tail boom, which is fantastic. And if you actually you can engage, you can actually give it a mass bump scenario. So if you roll it, it'll mass bump and it'll actually do the tail boom strike too. So if you guys are interested in this, he's selling them for like $40 delivered. They're awesome. I'll put his Facebook on in the chat. But yeah, these things are great. He did a great job for us. So anyway,
Yeah.
what do you got, Jay?
3D printed stuff. There's
Yeah.
some great designs on there.
Amazing.
I just wanted to talk about the enter in auto thing, and then the low G you feel with collective versus cyclic, and why I think that's a big difference. If you imagine, it's all about momentum of this airframe, right? So if you imagine you're doing 60 knots or whatever it is, and you push over, the momentum of the airframe keeps moving forward, and that's that disconnect between the fuselage and the rotor disc. Whereas when you lower collective, unless you were in a climb before you started that auto rotation, if you just dump the collective, the rotor, which is producing thrust, is now not producing thrust, and they're coming down together. I think that's the big difference. An interesting thing, though, is that the previous safety notice, before they updated it in August 2025, they specifically said that you could not get low G that could be related to mass bumping in an auto rotation entry, no matter how assertive and aggressive it was. And they changed that, and I probed G at Robinson about what changed there. And I think Robinson always has to be very, very careful. They misspeak about something, and it becomes an accident. It becomes a lawsuit point, right? And Robinson doesn't have to put those safety notices out. They put them out to keep the Robinson fleet safe and the pilots that fly them. But it also, they have to be very, very careful from a legal point of view that something they say doesn't, end up. I mean, Richard, for example, that's still an ongoing thing where there's been some accidents with the Richard maneuver, which they're pointing fingers at Robinson because at one point Robinson was really promoting that as a recovery technique, which is a side note to this what we're talking about. But so I understand why they have to be careful with that, so that they can't say something if there's an extreme example that could still lead to a low G mass bumping scenario. And I think that would be someone who is in an aggressive climb who enters an auto, because then there is still momentum of the fuselage moving up, and it doesn't matter that the rotor disc has descended into an auto rotation profile. They are disconnected, and if the pilot makes an input, it's going to affect the disc, not the fuselage, and that potentially will lead to mass bumping. But I think generally for most people, they're flying straight and level within an auto, or if they have an engine failure, you're not going to be concerned about slowing the collective down because of low G. You're concerned about loss of rotor RPM as the primary driver there. That's my 2 cents on that anyway.
Yeah.
Hey Jay, a great video that you put out with the auto rotation, your last video there. Also want to throw in, what do you guys think about Pete Gillis's cyclic back theory? I've ran into his video series recently where he highlights the importance of the cyclic back. I just wanted to hear some feedback from you guys. What do you guys think?
Talking specifically about the Robinson helicopters, right, Jay?
No, he flies other stuff, but he emphasizes the cyclic back as in, getting that air coming through just as important as lowering the collective. So
I don't think
that,
I'm quite familiar with that. If somebody could do
Yeah.
a quick recap of it.
Mm-hmm.
I'll tell you real quick, a couple of quick stories, because I teach this regularly at the flight school with our new instructors, and we demonstrate it in the sim and in the aircraft. There was an accident that triggered this discussion, I think, probably about 10 years ago. There was an A-Star crew, pretty well, 1,500 or 2,000 hours back then to get into the EMS world, and they have an engine failure, and they end up plowing this thing into the ground, and they never recovered RPM, even though they lowered the collective. And this was just about the time where Airbus were putting in like mini black box type equipment, so they knew what the collective and all the other inputs were. So Airbus took this into their sims, and they rebuilt the scenario, and they looked at what happened, and sure enough, engine failed or there's some sort of partial power failure, the crew recognized the low RPM and dumped the collective. And I can't remember if there was other circumstances like nighttime, MVGs, or whatever it was, but they dumped the collective. And we all know in about 2 to 3 seconds, that relates to a massive nosedive, right? The collective is going to change the pitch. And as it did that, basically the blades never got a true airflow up to maintain RPM, and this thing never recovered RPM. So what he's talking about is on a RPM is everything. We all know that, and we know that collective is the big driver on that. But if we simply just lower the collective, 2 3 seconds later, you're going to have a pitch attitude that will bring the RPMs down. And I've done this many times in the aircraft and in the sim. If you simply lower the collective in about 2 to 3 seconds, RPMs come down to about 90% in the R22 or R44. And your immediate reaction is, oh shit, low RPM. So you dump the collective even further if it wasn't already on the stops. But you haven't solved the problem. The problem is you aren't presenting the rotor disc to the vertical flow that needs to come up through the rotor disc. And I can imagine if you're under MVGs or at nighttime, that would have been very hard to perceive that was going on there. If they hear the horn, where do their eyes go? Where does everyone's eyes go? Into the tacks. So it's I teach it as an instructor error because it's a kind of a trap as far as the instructor goes. If the student lowers the collective but doesn't adjust the attitude, doesn't hold the attitude, horn goes on, both the instructor and student look to the tack, everyone lowers the collective because they may have done a little catch, and they lower the collective, and the next thing they see is airspeed now racing up to 80%, and they come off cyclic, and that's an overspeed. They recover the RPMs too aggressively because now they have 80 knots of energy, which is way, way higher than 60 knots, and the last thing they did was dump the collective to the stops. So, in about 2 seconds, that alone is going to bring things up. We do it as more of a sort of an instructor intervention trap to watch out for. But going back to this, the original thing he was talking about 10 years ago, it has killed people. And that A-Star accident, if I could think of the company that you guys look up, is I think the pivotal accident that kind of really drove this arc cyclic movement. Or cyclic input, I guess. Yeah. Rant over.
Jay, following up from that, I guess I've seen recently Claude Bouchard came up with his Bouchard technique for auto rotation, which I know it's a contentious point on itself. I get it. There's a lot of debate about in the industry, but I guess my question is, relating it to that precisely our pull on that cyclic to recover the RPM, right? What he's proposing is a shallower angle of flare, which works very well in heavier aircraft with higher inertial rotor systems, like the A-Star, right? That technique works perfectly in there. But for us, Robbie Rangers, as we've been called, right? Which I disagree with the term, but sure. For us, in lower inertial rotor systems, would that technique, in your opinion, serve a purpose? Would it bring us more energy or less energy at the finish of that auto rotation?
This is just I've flown A-Stars, 407s, all the light turbines, EC-130s, and they're all different. They're all different, right? So, a 407 will flare different than a 206 versus a R22, R44. But even within the type, every flare is different. The DA, the airspeed, the weight, everything else. I always think of flares at 2 stages. First stage is stop the descent. You have 1,500 feet per minute. You have to stop the descent. So you do whatever it takes to stop the descent. Second stage is maintain RPM while bleeding off airspeed, and that is the real variable. Because you take a low rotor RPM inertia system like the R22, it is very sensitive. It'll decay very fast. But the good news is you can just crank it up a little bit with a cyclic, and you maintain it. The downside, of course, is you deal with overspeeds a lot more with aggressive flares. But I remember watching that video, back to the Bouchard auto technique. It didn't present anything to me I hadn't seen before, in that we just modulate the flare to preserve rotor RPM and not hit the ground and deplete airspeed. I didn't see anything magical or new. I think that was part of the contention, was everyone was like, "That's a flare." You can put a name on it, but that's a flare. And every flare is different. So if I take an R22 and we come in at 75 knots in the summer, well, we're going to start the flare a little bit sooner because you have to dissipate that energy. If we come in and we have thermals and we drop out, we got to crank this thing up, or it's a go around. We got to try and get the engine in. So I don't know. I just I I don't want to speak badly of any pilot, but I just didn't see something magical about that technique that hadn't been part of your toolkit of, like, we've got to make every flare individual.
I guess, my whole point of bringing it up is just the fact that there's a lot of contention about it, but also wanting to see what the different perspectives in the industry were, right? Just as we're doing with every other topic so far. But it was just interesting to see it as a technique, and something applicable for every situation, basically, which didn't seem as logical to me.
Did you find that if you ever tried to do this in the R22, you could maintain RPM and have satisfactory RPM at the end?
I flew two different helicopters. So I tried it in the 22, I tried it in the 44, and most recently on the Enstrom. So I flew an F-28 recently, and very high inertia rotor, lovely to auto rotate. I find that in the Enstrom works wonders. I tried it at different speeds. I tried a little bit faster, so that one's miles per hour. I tried to start the flare at 70, and then at 50, to try different things, and it works wonders. Now in the 22, I find that I end up with lower RPM at the bottom when I'm about to derotate to set it down.
Yeah. I mean, I remember going into the A-Star for the first time. I think the A-Star or the EC-130 was the EC-130 was my first aircraft out of the Robinson fleet, and the R-22 profile did not work for that aircraft. That would not work. And so I understand. If you're primarily looking at something like an A-Star, that flare's profile is kind of the standard for that aircraft.
Yeah, I mean, when I did my transition course about, I don't know, that probably was like 10 years ago, into the EC-130, I flew with Jacques Delong, who used to be the chief flight instructor for a Eurocopter back in Mexico. He mentioned that helicopter doesn't really like very high flares. If anything, very shallow at 75 feet, and then derotate to harvest all of the energy. And that kind of stopped. But when I came back to lighter aircraft, it was just a surprise to say, wait, I have to readapt now all of this to what I'm flying now. Yeah.
I think it truly depends on what airframe that you're flying in. Thinking about like how big a Black Hawk is compared to like an R-22. Talking about the cyclic back technique, and kind of walking through my head like, okay, how do I teach my guys how to do enter into an auto rotation? One constant that I think can be applicable to all airframes is the steady state factors that we have to be reached before that 300-foot threshold that we were talking about, because we hold ourselves to the same standard. We look for RATs, which is rotor within limits, airspeed, aircraft and trim, and safe area for landing. So the biggest thing, like what you were saying, Jay, correct? Helicopter training videos?
Yeah, there's two Jays here,
Yeah.
Sky
Okay.
and myself, yeah.
Okay. Just make sure I had it right. So I think the biggest thing that like to focus on there, especially with the cyclic back technique, falls on that first piece of making sure that the rotor is within limit, and knowing your airframe and knowing what that airframe requires to get to that limit. Talking about like mast bumping and low G maneuvers, I remember training with my flight school instructor, Rodney Lacewell. He flew in Vietnam, was probably about 70 years old when I was flying with him. But he had a lot of experience in a Bell 206, and man, he could make that airframe absolutely dance. And I remember doing low level 180 auto rotations with him. So when we talk about low G maneuvers, risk of mass bumping because the Bell 206 uses that same teetering rotor system. Um, there was never a risk there. I remember that we discussed mast bumping when I was going through flight school. So like with the Bell products that the Army used to fly, and really it was in those situations where kind of like what you were saying, Jay, that the airframe, the fuselage, and the rotor disc are almost acting independently. When that rotor disc is not supporting the load of the fuselage underneath it, that's really when you get into the risk of you make that input, the inertia of the airframe wants to keep going, and the rotor disc just does what it wants to. So when that rotor disc isn't supporting us is when we really have to worry about that. And then going back to the rotor, or sorry, the auto rotation technique there of cyclic back. To give an example, like when we auto rotate in a Black Hawk, we're looking at like about 2,000 feet per minute rate of descent. Fairly typically, we also, though we aim for it, we don't go all the way down. We'll start approaching that, but to maintain that rotor in limit, we often have to increase collective just a little bit, and we're typically flirting on the very edge of like what that of an overspeed. So like keeping it from going over 105 for NP. Um, Thinking a little more on that, like we typically aim between 80 knots and 100, and 110 is our max glide distance. So when you consider cycling back, depending on what the situation is, where that safe area is to land that you're trying to get to, you may not want to trade off all of that forward airspeed when you're trying to push a little bit further. Say you were just short of a safe landing area, had a flight over water, you lost your engine, as you might be given a tour in Destin. I've seen them using R44s out there for that. You lose your engine, you go into an auto rotation. If you commit too much to that aft cyclic, yes, you may have loaded up your rotor system, and you may have a good auto rotational rate of descent. But that's sort of why we go in that order of rotor. Okay, rotor's good. Airspeed. Do I need to push this forward or keep it where I'm at to adjust for that safe area to land? And trim kind of falls somewhere in there to make sure that you're going smoothly through the process. But truthfully, that balance between rotor and airspeed ensures that you're going to make it to that safe area to land. So it really does come down to what airframe you're flying, because an aggressive aft flare on a Blackhawk, man, that tail rotor is like 25 feet behind me. If I try to do an aggressive flare at the bottom of an auto rotation, I could be breaking off the tail rotor back there. So once again, do what is appropriate for your airframe, and be that professional that digs into it, digs into the manuals, watches videos, attends helicopter pilot study group sessions that talks about all this stuff. It's continue your education and continue to learn and know what the situation calls for.
Michael, you read my mind on the the too aggressive aft cyclic in an auto rotation. I was going to talk about that, and I wanted to get your guys' opinion. We generally enter auto rotations between 60 and 70 knots. 75 being kind of the ideal spot. I think a lot, or 65 being the ideal spot. And I have seen, and I've been guilty of, we down right and we aft. And then when we pull aft, sometimes I've pulled hard enough where I've slowed that airspeed down to 50 knots. And then what happens when you're at 50 knots? You push forward for airspeed. And then when you push forward for airspeed, what happens? So you get into this chasing scenario, right? Where you're running the reins on the collective and the acyclic. And so I've recently been far less aggressive on that aft cyclic in my auto rotations, if any at all, frankly. I mean, just enough to, so it's like down right, and then, we want to aft just a touch to reload that rotor disc. But I'm also like kind of really immediately focusing on airspeed over RPM essentially at that point, just to make sure I'm still in that 65 to 70 range. And once I kind of paying it, I'm comfortable with I'm established. I have good RPM. I have good airspeed. Then I'll kind of take my eyes off the gauges and fly it. But I've fought that quite a bit, putting too much aft cyclic to load that rotor disc, and I think that's just a. And I also want to ask you guys about altitude, doing this at altitude. So we know at sea level it's a
Yeah.
little bit different animal, right? But where Jay
Yeah.
is, and he could have 7,000 DAs. Um, uh, Pulling aft is going to be a little bit more important. At high DAs, you want to have a little bit, you want to load that rotor system a little bit faster, and you want to probably roll off throttle as you're lowering collective, right, Jay, at altitude?
We do two things to deal with that. Well, first of all, our procedure is all the way down, roll off, and then catch while we're doing
And then bump.
auto training.
Yeah.
Mid engine failures are different. We'll announce engine failure whilst rolling down. But if the horn goes off before the student reacts, the instructor takes the controls, dumps the collective, and ends the auto. But the only real sort of thing that we do when the DA gets up, because in the winter we're minus, we're below 0 Celsius, but in the summer, the highest we'll see is sometimes 40 degrees. What is that, 100 Fahrenheit or something like that? So when the DA gets above 6,000, the indicated airspeed is so much in error for the actual true airspeed. Our biggest concern is that if we didn't adjust anything, we would be coming down to the flare with about 10 knots more airspeed than we're expecting. And because the indicated and true is so different in those high DA days. And because the air is thinner, the rotor moves faster. So to prevent overspeed scenarios, once we get above 6,000 DA, we take our target airspeed and just knock 5 knots off. And that kind of translates back to closer to what you're doing in spring and winter and fall. So we kind of modulate it that way. But as for entry speeds, I think it's really, there's two different things. There's two different maneuvers, right? There's the teaching order rotations, standardized, slow, methodical, and right, great, you've got that. Now we go into the simulated engine failure type stuff, and there the airspeed should be, whatever you're doing. The airspeed does not. What's your cruise airspeed in R22? It's probably 85 knots. If you've never seen an auto rotation from 85 knots, that's not great training. So we start expanding the speed limit or the speed range on entry. The 200-foot checks are still the same. We have to meet those. And as an instructor, we have to understand that 85 knots in the summer in a turn after they've just made a radio call, that's high risk. We got to be careful there. But we have to build the range and not just kind of go for, all right, it's 500 feet again, it's 65 knots, we're on final. We have to, expand their capability. And there's some like blending between the two, because there's simulated engine failure, which is pretty shocking for a student, engine failure, and then there's you do another auto. We need to also cover that stuff in between. So, hey, we're going to do an auto today, but we're going to do it from 700 feet on a left base at 75 knots. Now we're going to try or 80 knots. We're going to try to start expanding their normal entries so that when they get simulated engine failures, it doesn't phase them. I mean, the worst I've ever done, and I'm not sure I'd do it anymore because I have kids and I'm older now, but I remember back when I was an instructor first time round, I had this cocky student who I loved him. He was great, but I would wait till he was making a radio call and I'd give him an engine failure on a radio call. It was amusing for me and everyone else. He didn't find it very funny. I'm not sure I'd do that anymore. I probably wouldn't recommend that to my instructors, but anyway.
We can cut that part out of the recording.
Yeah. But one part, John, that I wanted to, and I think Jay kind of hit up on it, when you said prioritizing the airspeed. I think when we're academia, that sounds good, doing the 60 to 70.
Yeah.
But when it comes to real life ops, never give up the RPM. Airspeed does not matter. RPM is it, so
Life.
yeah, it's life.
Yeah.
So anyhow,
And
good time to
adding, adding to what Jay.
good time to plug in the webinar. It's coming up quickly at us on the 23rd. So if
Yeah,
if you want to throw that in, John.
Yeah, Jay has a fast webinar with Richard Morrington Sanford, the author of Keeping the RPM in the Green. That's going to be on Saturday, May 23rd. I will put a link in at some point in the Max Performance channel.
And do some of those AI posters you did, John. Make some more of those. I'll put some of those around as well.
Okay, yeah,
that'll be awesome.
For the fast discussion, we'll do.
Yeah, because I think he's awesome. And great job, Jay, getting that organized. By the way,
Certainly.
Yeah, thank you.
Yeah, you bet. Well, we can certainly continue. Is there anything anybody wants to add specifically? We're coming up on an hour and a half.
I'm flat.
I just wanted to add something short to what Jay, the other Jay, not Jay from Helicopter Training Videos, was saying.
Oregon Jay and Florida Jay. That's how we'll have to distinguish ourselves.
Oh, he knows this Jay. I used to work.
Oh no! We know each other well. I mean, I did Jay's last flight review not too long ago.
Nice.
Yeah.
Was it January? Yeah, January or February. I can't remember which one of the two. So adding to all of that, I think that it's very important scenario-based training. I think it's definitely one thing that I'm big at the school. Number one, it costs less than the helicopter to run it, right? Number two, it's less risky inherently, right, than doing all of the maneuvers that we wish we were half the pilots that we could to do it. And number three is just a matter of we can't really simulate low G mass bumping. Going to our original topic, I guess we got really sidetracked here. Low G mass bumping, we can't simulate it. We're prohibited from doing so legally. We're prohibited from doing so in the manual, and in the interest of safety for ourselves and our students, we shouldn't do it. But and this is something that in the factory they were big at not too long ago, and I think Jay, you were there when Bob was telling us this last time. Even when you're flying the helicopter, if you're at 80 knots, if you are at 90 knots in the 22, which is a high speed range for us in that helicopter, he would simulate it by just having a big roll to the right and putting the student in that surprise situation by rolling the helicopter to the right and then having recover. Mm-hmm. And I practiced it since I got my instructor rating. And unfortunately, I find that most pilots I fly with, the first 3 or 4 times will always correct to the left. And I don't think that there are enough instructors preaching that, that we should create not a reflex necessary, but a reaction to what we're seeing, to what we're analyzing as pilot in command, and to be able to pull that cyclic gently, F cyclic, right? So I guess that's the only thing that I wanted to add there.
That's that reaction versus response, right?
Hey, that's really important, actually. I've just sent a link in the chat, guys, to a video you can jump to. It's about the 8-minute mark. We're not required to do flight training low G at all, and of course we can't. But I really believe that when they updated the SFAR in August of last year, they missed a point. Instead of taking away, what they should have said is, because there was a disconnect, right? You can't do low G, but SFAR said you're supposed to do flight training. And instead of just taking it away, what they should have done is said, let's train low G recovery. Mm-hmm. And I'll send you a link real quick for you guys to have a look at. The way we do it at our school is we run through the whole. Imagine you get light in a seat, and then the instructor will give you an uncommanded right roll. And now, if we're flying symmetrical, we'll go left or right. We could go either way. Mm-hmm. What are you going to do? And we do the whole training on the instructor to make sure they guard the cyclic on front and back, make sure they don't aggressively come back too much or whatever. But if you don't give them that visceral feeling or that imagination of that feeling and that uncommanded right roll, you're just rolling dice on whether they will try to do the right thing when this aircraft rolls left or right. I think the new symmetrical stabilizers can make a big difference, and we won't see so many of these anyway. But still, I still think it's really valuable. Once they get the uncommanded left or right roll and they come general aft and they fix it, then we follow it through with the rest of the safety notice about low G. It's like, well, what are you going to do now? Are you going to speed up, slow down? You should be 60 to 70. You should be getting away from what caused it. You should think about landing if you're surrounded by thunder cells. I still think that flight training is really important. We can never and will never push forward, but we can talk about the imagine you feel, and then kind of follow on with that, giving them the uncommanded right roll. You also have to point out to them the cyclic won't move like this, of course, but I'm having to create this right roll. And depending on the student is how far you take that. A commercial student, you can quite an aggressive right roll. Brand new student, you probably, what you want to do is scare the shit out of them. But I think they should. I really think they should have kept that in there. I think it was a mistake to completely get rid of it. I understand why, because it completely conflicted with the no low G limitation. But anyway.
Thinking about the aerodynamic forces at play here, if as we discussed earlier, in those low G maneuvers, that the fuselage and the rotor system are essentially, as best way I can describe it, disconnected by physics, that the rotor system's no longer pulling the fuselage along, and I'm not a Robinson guy by any means, but would an increase in collective before applying cyclic movement help in some certain circumstances to try and reassert that rotor disc's control authority over the fuselage?
I've asked the same question. I've also asked whether you would put left pedal in. Would that make a difference when it was more an emphasis on the tail rotor thrust? But I think in the moment when the shit hits the fan, the only consistent thing that they've said is gentle aft to reload the rotor system. The other thing about, if you think about whatever flapping's happening, if you raise the collective, you accelerate whatever force is working on the rotor system, and perhaps that's why that's never been a suggestion. Or even if you lower collective on the downward side, perhaps you're accelerating that movement of the disc. But I always thought it was really interesting and pretty hard to explain to a student, why is it the left and right cyclic is a bad idea and it doesn't respond with the fuselage, but aft cyclic, it responds to that. I always find that a little bit hard to explain. Robinson have just put out a low G and mast bumping standardized lesson. It's pretty in depth. I put some in
Max Performance.
Chat, a couple of days ago, I put some excerpts in that. And they're putting it out to their Robinson certified instructors, those ones that have gone through the Robinson standardization course. And it really goes deep dive. I've never seen anything quite like it, how far it goes into the subject. I would have put it in here, but they are not putting it out to the general public yet. It's only to their instructor, the instructors that have gone through the course. But I mean, there's some deep dive into some physics about what's going on there. And there's talk about induced flow and things like that and how that affects it. I'd never thought about that, and I found myself very much educated by that document. I'm hoping they'll put it out to the public soon.
It's great that there's so much to learn. I'll be doing that course at some point in the next few, hopefully next 3 to 4 months. So we'll have a study group and I'll recap on that. But I'm going to first come fly with you, Jay, in Oregon.
Yeah, I was actually thinking about it just yesterday and today. I was trying to work out the times and all the costs and everything you want to. I'm looking forward to it.
Yeah.
And Stephen, you did a great job. You led us really well today. I gotta say, you did a really great job. Private pilot, you surprised. If you didn't say that, I think people would think you were a CFI. Really good job.
True. You should be proud of yourself.
Thank you very much.
Keep up the good work.
Yep. Absolutely.
Yeah. Well, guys, I think it's a good note to end on. Cheers to Stephen. Give yourself a pat on the back. Really leading this really informative discussion. It was a lot of fun. That wraps up Helicopter Pilot Study Group number 17. See you guys all for 18. Have a great one.
You too.
Good one.
Everyone, good job.